Okay, so we're going through the chemistry paper from 2020, the higher paper to start with. Okay, we're going through each question and explain to you how I get the answers and why I get to them as well. You should pay attention and fill in your paper as we move through. Question number one wants two substances that want intermolecular forces between them. Now, intermolecular forces are found between any substance as a small covalent substance. So here, the only ones that are small covalent substances are polyethene and water because it's H2O, and polyethene because it's ethene molecules, which is C2H4, and there's then lots of those joined together into one big long chain, but there'll be lots of those chains near each other attracted by intermolecular forces then. The second question shows you this image of three different substances and shows you their structures. Your job was to compare the structure and bonding of these three compounds. Now you can clearly see that this substance has got a lot of atoms all very close together. That means that this is a lattice structure, and because it's magnesium and oxygen, a metal and a non-metal, this will be an ionic substance. Carbon dioxide is a small molecular covalent substance, and silicon dioxide is a giant covalent structure. We can tell this because of the straight lines going between them. Whenever you can see lines between things like this in giant structures, silicon dioxide should be covalent and carbon dioxide should be covalent as well. If we're going to compare the structures of these things, we know that carbon dioxide and silicon dioxide are made of atoms, whereas the magnesium oxide is made of ions because it's ionic. We know that silicon dioxide and magnesium oxide are giant structures. Because that lattice is giant, and we know that giant covalent substances are obviously giant structures. And that means CO2 is a small structure. All three compounds here have strong bonds. Apologies if you can hear my cat in the background purring. And carbon dioxide and silicon dioxide are formed from non-metals only. So it's covalent. Whereas magnesium oxide is made of metals and non-metals. So ionic. We could also look at those bonds involved in these diagrams. You can clearly tell that in here, we only have those single bonds, whereas carbon dioxide has got those double bonds. So carbon dioxide has double bonds. Silicon dioxide has single bonds. And we could talk about the fact that there'll be electrostatic forces in magnesium oxide. It's also worth mentioning, because this is ionic, it means that electrons were lost or gained. Specifically, they were actually sent from the magnesium to the oxygen. We know metals lose electrons and oxygens gain them. In question number 2, it says the questions are about metals and the reactivity series. So our job here was to go through and explain two statements about most transition metals that are correct. And we should be aware that transition metal elements form ions with different charges. And we should be aware that they have high melting points because they are metals. Question 2.2 said a student added copper metal to colourless silver nitrate and they observed pale grey crystals forming and a solution turning blue. Well, that pale grey is actually that the crystals are silver. And that's because that silver in the silver nitrate is being displaced by the more reactive copper. So the copper ions are blue. And this happens because copper displaces silver. Question 2.3, so the student's given three metals X, Y, and Z, and it says the metals are magnesium, iron, and copper. Plan an investigation to identify the three metals by comparing their reactions with dilute hydrochloric acid. Well, first of all, we should have at least a good idea of their reactivity. We should know that magnesium from group 2 is the most reactive. We should be aware that copper is very unreactive, and iron is sort of in the middle of the two. So all we're going to need to do here to test these is add each metal to a specific volume of hydrochloric acid. And we're going to do one of three things. You could either measure the temperature change, or you could compare the rate of bubbling, or compare the colour of the resulting solution. I'm going to go with measure temperature change. You could talk about measuring before and after the reaction, and that would give you good results here. The next thing to make sure that you mention is that you would then see for copper, no reaction. So we'd see no temperature change, because copper's really unreactive. For the iron, you would see small temperature change, and the magnesium would change by a temperature by more than iron. Control variables here is the amount of these acids that we're using, and you're making sure you use that same concentration each time you do it, and the same mass of metal added each time as well. So you could say add 1 gram of the metal to 20 centimeters of hydrochloric acid, and as long as you're doing that each time, your results are going to be equal each time. So I need to do these things because it says to plan the investigation. So I've planned the investigation. So I'm going to add 1 gram of each metal to 20 centimeters cubed of hydrochloric acid by comparing their reactions, and we should give valid results. So you literally have to tell them what the results would actually be as well. Question 2.4 shows you the numbers and percentage abundances of the isotopes. Now, to work out the relative atomic mass, all we've got to do is multiply each of these by their percentage abundance and then divide them by 100. So we're going to do 203 times 30, because that's 203 and 30, and we're going to plus 205 times 70. And we're going to divide that by 100, and that will give you an answer of 204.4. And there's no units to that because relative atomic mass is relative comparative, so it has no units. And interestingly, anytime you're doing this one, they'll literally give you a mass number and abundances. All you do for the element you're working at is you take the mass number, multiply it by the percentage abundance for all of them, add them all together and divide them by 100, and it'll always tell you the relative atomic mass by doing that. Question number 3.1 says a student investigated conservation of mass. You had to explain how the results demonstrate the law of conservation of mass. Well, the law of conservation of mass is the idea that in reactions, mass is never lost or gained. So really, we'd be looking for the fact that beaker A contents and beaker B contents are the same. They haven't changed in total. So what we'd need to do here is work out how much they've increased by over the course of this reaction. So we do 8.22, take away 78.26, and we do 78.50, take 48.54, and this would both give us the answer of 29.96, because the overall amount of those substances has not changed. And then we'd say no atoms lost. Conservation in general means you're not losing things, and we've just proven that by proving the mass before the reaction and after the reaction were identical. Question 3.2 says suggest how the student could separate the insoluble silver iodide from the mixture at the end of the reaction. Well, we have an insoluble substance in a mixture. It's a liquid. So we're going to filter it. Simple as that. One impurity that's removed by rinsing with water. We're looking for anything that dissolves in water. So we could say the sodium nitrate. Well, why did they warm the nitrate? And they did that to evaporate water. Question number 3.5 said equation of reaction is silver nitrate plus sodium iodide plus make silver iodide and sodium nitrate. Give the answer to 3 significant figures and calculate the percentage atom economy for the production of silver iodide. Well, silver iodide is this one, so we want to know what percentage of these products is silver iodide. So we need to work out the mass of silver iodide and the mass of silver nitrate, which they've helpfully given to us. And all we're going to do with those is add those two things together to get our total mass in this reaction. So if we do 235 plus 85, it gives you an answer of 320. And then we're going to do the mass of silver nitrate divided by that total mass in grams. So 235 divided by 320 times 100, because we want this as a percentage. And that will give you an answer of 73.4%. All atom economy wants you to tell them is what percentage of the things you're looking at, so the total, all the products, what percentage is the thing that you want. In this case, we want silver nitrate. We've got the masses of those things, so we just worked out the percentage to be 73.4%. That's all we need to do there. Question 3.6 says, give one reason why reactions with a high atom economy are used in industry. Well, because they are more sustainable. It means you're making more of those products based on the reactants. You have a low atom economy means what you're making a very small amount of what you want and wasting the rest of it. Other possible answers here are a very broad economic reasons, just because we want to save money, it's cheaper, and produce a high percentage of useful products is also good. So it produces higher percentage of useful product, which is obviously the desired outcome. Is you want to make as much useful product as you possibly can. Irritating, that's following me down the page. Anyway, number 4, questions about electrolysis. A student investigated the electrolysis of copper chromate solution. Copper chromate solution is green. Copper chromate contains blue coloured copper ions and yellow coloured chromate ions. Student switched the power supply on. The student observed the changes at each electrode. The student saw that at the positive electrode, the solution turned yellow. At the negative electrode, the solution turned blue. Bubbles formed at the electrode and a solid formed at the negative electrode. Well, because it's the negative electrode, we know that the solid is probably going to be some kind of metal. We just need to work out what that metal might be. Let's look at the actual question though. Why did the colour change at the positive electrode? Well, if we look back at the top of here, we know that chromate ions are yellow and our solution turned yellow. So our solution must have turned yellow because chromate ions moved to the positive electrode. And they did that because opposite charges attract. It's opposite. For some reason, it's not saved that. The gas produced at the positive electrode was oxygen. The oxygen was produced from hydroxide ion. Name the substance in the solution that provides the hydroxide ions. We should be aware, because our substance was copper chromate. There's no hydroxide in copper chromate. The only substance there is hydroxide ions in there is water, because it's dissolved in solution. How does the solid form at the negative electrode? Well, we know that our solid is going to be the metal, and our metal was copper. So copper, when it forms at that electrode, copper gains 2 electrons. And it gains them because in solution it is a 2+ ion, so it lost 2 electrons to become that. So when it forms at the electrode, it loses its charge, and it will lose that 2+ charge by gaining the 2 electrons back, and it will form copper atoms. Question number 4 says a student repeated the investigation using potassium iodide solution instead of copper chromate. Name the product at each electrode when potassium iodide is electrolyzed. Well, we should be aware that potassium is far more reactive than carbon is. So we know that Far more reactive than hydrogen is, sorry. So we know that we're going to get hydrogen forming there because at our negative electrode, you always get whatever the least reactive is out of hydrogen and the metal when they're dissolved in solution, and this is in solution. And we know at our positive electrode, we have a group 7 substance, which is iodine. So iodine forms, because our rule is anything in group 7 will form at that positive electrode, and that's always going to be the case. Next question then, number 5, says the questions about the development of scientific theories. The plum pudding model did not have a nucleus. Describe 3 other differences between the nuclear model and the plum pudding model. So the first one is that it's mostly empty space. The positive charge is all in the nucleus in the nuclear model. And finally, the mass is concentrated in the nucleus as well. You could also mention earlier that electrons and the nucleus are separate also. That's another valid thing for you to mention here, but I'm not going to write that down. Question 5.2 said Niels Bohr adapted the nuclear model. Describe the change that he made. Well, he said that electrons orbit the nucleus. And he specifically mentioned that he did this at specific distances. We call those distances shells. You could just mention the electrons are in shells around the nucleus. This is also fine, worth those marks as well. Question 5.3 said Mendeleev produces periodic table in 1869. He arranged the elements in order of atomic weight. He then reversed the order of some pairs of elements. A student suggested Mendeleev's reason for reversing the order was to arrange the elements in order of atomic number. Why can't that be correct? Well, the atomic number is the number of protons. And protons weren't discovered yet. Question 5.4 said, give the reason why Mendeleev reversed the order of some pairs of elements. Well, he reversed their order so their properties match the rest of their group. Question 6 was about displacement reactions. We should know displacement reactions when a more reactive element replaces a less reactive one in an element. What's meant by the term activation energy? Well, this is the minimum amount of energy required for particles to react, or for the reaction to occur. Yeah, either of those things is fine. It says, for question 6.2, a mixture contains 1 kilogram of aluminium and 3 kilograms of iron oxide. The equation for the reaction is 2Al is Fe2O3, makes 2Fe and Al2O3. Show that aluminium is the limiting reactant. We want to show that aluminium here is the one that's going to run out first. So we are going to show that you need more iron oxide than you do aluminium. So we are going to, first of all, write out our equation. We're then going to actually split it into a table to make our lives easier. So here we have got mass, molar mass, number of moles, and the ratio of those substances together. And I've done this because I'm going to use this to show that we have got too much aluminium in this because it's the limiting reactant. It will run out first, is what I mean by that one. So we've got not enough aluminium, sorry, we've got too much iron oxide. So we don't need either of these two things because they're not relevant to this, because we're only looking at the aluminium and the iron oxide that it's reacting with in this reaction. So we first of all need to know the molar mass of aluminium that we have. So aluminium's molar mass is 27. And we know that iron oxide's molar mass is going to be 56 times 2, which is 112, plus 16 times 3, which is 48. So it should be 160. Just double check that one on a calculator. 6 times 2 plus 160, I am right. And we know that we've got a kilogram of aluminium and 3 kilograms of iron oxide. Well, either way, we can use either of those two to work out what the amount should be, because all we're going to show here is that you have not got enough of one of these substances, how much it would actually react with. So if we go with our aluminium, we've got a kilogram of aluminium, and that's 1,000 grams. So if we've got 1,000 grams of aluminium and 27 is the molar mass, we're going to do 1,000 divided by 27, which means we've got 37.03 moles of this substance. And we know that it's a 2-to-1 ratio. So really 37 moles of that should react with half that amount, and 37 divided by 2 is 18.51. The interesting thing about using this table is when we come down the table, we can divide them. When you go back up the table this way, we're going to multiply those two things together to work out how much iron oxide that actually should react with. So we can do 18.51 multiplied by 160, and that should react with 2,961.6 grams. Now we've got 3 kilograms, we've got 3,000 grams, so we actually haven't got enough aluminium oxide here. Sorry, I haven't got enough iron oxide for that reaction. We've got too much iron oxide. We don't have enough aluminium to react with all the iron oxide that we have, and that means aluminium's going to run out first of all. So that means aluminium is then our limiting reactant. So we can say aluminium will run out first. We'll spend more time using these tables to predict this reaction, because using the table makes this much, much simpler. Because if with that number should here, this should be 3,000. If that was 3,000, we'd know that there's the right amount of each. Because it's less than 3,000, we know we haven't got enough aluminium oxide to react with it. Question 6.3 asks you to finish off this ionic equation. And so all we need to be able to say is what's happened to these substances. So we know that we've started off with magnesium and zinc as what's happened, because magnesium has displaced zinc. The magnesium originally wasn't in a compound and the zinc was, and at the end magnesium will be in a compound and zinc won't. So that means our zinc will have been kicked out of the compound and will now be a solid, and our magnesium will now be in the compound and now will be an ion, and that means it will be aqueous. And that's how this always works when it comes to ionic equations. Question 6.4 says, explain why the reaction between magnesium atoms and zinc ions is both oxidation and reduction. Well, we know that oxidation is the loss of electrons and reduction is the gain, because of our phrase oil rig, and magnesium was oxidized because it lost electrons and became 2+. And if magnesium is oxide, it means zinc was reduced because it gained electrons to stop being an ion. Question number 7 showed you this image of a reaction profile. It said there are 2 errors on this reaction profile, and we had to say what those 2 errors are. And we know that the activation energy should be from the reactants to the peak. And the other product here is that because this is a reaction between hydrogen and oxygen, which is an exothermic reaction, in an exothermic reaction, the products should be lower than the reactants are. because we know things reacting with oxygen tend to be combustion reactions when they're non-metals. The reaction between hydrogen and oxygen is hydrogen fuel cells used to produce electricity. Hydrogen fuel cells and rechargeable cells are used to power some cars. Give 2 advantages of using hydrogen fuel cells instead of using rechargeable cells to power cars. Well, the hydrogen fuel cells have no toxic chemicals to dispose of. They take less time to refuel. You can travel further before refueling. And finally, there's no loss of efficiency over time in those. Batteries tend to get worse. These ones will not do that. The reactions occur at the positive electrode and at a negative electrode in a hydrogen fuel cell. Write a half equation for one of these 2 reactions. We're just going to show the one for hydrogen forming. So we're going to go from our hydrogen, no, that's wrong, from our hydrogen molecule, and we're going to make that into hydrogen ions. And we're going to have 2 hydrogen ions that are positive and 2 separate electrons. And this is going to be our negative electrode in this reaction, because we've obviously got water that we're working with here, so we're going to have hydrogen forming at that electrode. 7.4 says the 3 states of matter can be represented by a simple particle model. Figure 4 shows a simple particle model for hydrogen gas. Give 2 limitations of this simple particle model. Well, hydrogen here is not shown as a molecule. We know that hydrogen's H2, so each of these should be 2 atoms of hydrogen together. It also says the particles are shown as spheres. And we know that based on our atomic model, they shouldn't look like a sphere. They should have shells, a nucleus, and that's what they should look like. They're shown as solid. It's another acceptable thing to mention here. We know that they're mostly empty space. These dots don't show that empty space in any way. We don't show the intermolecular forces between each of these atoms. You could also mention it's only 2-dimensional as well. Also, not great. Question 7.5 says the hydrogen gas needs to power a car for 400 kilometers, would occupy a large volume. Suggest one way it can be reduced. We can put it under high pressure. Condense it, increase the concentration, store it as a liquid is fine, allow develop more efficient engines is also good based on what the mark scheme says. Question 7.6. So for this question, we'd say the energy needed for a car powered by a hydrogen fuel cell travel 100 kilometers is 58 megajoules. The energy released when 1 mole of the hydrogen gas reacts is 290 kilojoules. The volume of 1 mole of gas at room temperature is 24 decimeters cubed. Calculate the volume of hydrogen gas at room temperature and pressure needed. So we need to work out how many times 290 kilojoules goes into 58 megajoules. So first of all, we need to turn kilojoules into megajoules. Now, there is 1,000,000 joules in a megajoule and 1,000 joules in a kilojoule. So we're literally going to divide our kilojoule by 1,000, and we know that we have 0.29 megajoules. We're then going to do 58 megajoules divided by 0.290 to give us how many times they go into each other, and that should be 200 times. So we need 200 lots of 1 mole, and each mole takes at 24 decimeters cubed. So if we multiply those by 24 decimeters cubed, it will tell us that we need 4,800 decimeters cubed in order to use those. And that's what our answer should be to question 7.6. Question number 8 says it's all about the halogens, and it says what state is bromine at 0 and 100 degrees? Well, we know that if we look at the bromine here, the -7 is when it melts and it boils at 59. So at 0 degrees, it is above its melting point. This means that it will have gone from a solid into a liquid at this point. So it will be a liquid at 0 degrees, and 100 degrees is over 59, and this means it will have boiled at this point. This means it will be a liquid and a gas at those 2 temperatures. If it helps you on a question like this one, I always tend to put -7 like this, put 59, like this, and then I write down for myself that solid is what it will be below that, liquid is what it will be between those temperatures, and a gas is what it will be above that last temperature. We know that 0 sits here. We know that 100 sits here. So we can then easily work out whether we have a solid, liquid, or a gas. That just helps me. Might be useful to you to remember when it comes to answering a question like that one. Question 8.2 says, explain the trend in boiling points of the halogens shown. Well, boiling points is all to do with these substances. They're intermolecular forces because these will be non-metals. They're all molecular substances. They're all diatomic. They all come in pairs. The boiling point in these increases as you go down the group. We know this because the relative mass increases down the group. We know bigger things are at the bottom of the periodic table. We know that bigger things also have got a higher, stronger intermolecular forces. I should say intermolecular. That's not what I've written. And finally, we need more energy to overcome those stronger forces. Because they're stronger, they need more energy to overcome. Those are your 4 points to make. That's what your 4 marks are for. And that's your point here. Why is it not to correct the boiling point of a single bromine molecule is 59 degrees Celsius? Well, a single molecule of anything can't be a solid, liquid, or a gas because we need to have lots of these molecules together for any of these properties to apply. Now, we call this idea that this is a bulk property. Boiling and melting point are bulk properties. They're properties that only exist when you have got lots of atoms together. Okay, so a single atom will never have a boiling or melting point because it can't boil. It's already separated from everything else. Question number 8.4, so give one reason why this experiment should be done in a fume cupboard. Well, the reason why we do anything in a fume cupboard is the gas is toxic in this case. Usually it's some reason like this one. Harmful, we find to say. Poisonous is fine to say. Prevent inhalation of the gas is fine to say. If you're doing things in fume cupboards, any of those are generally the reasons why you're doing it. It's going to be harmful. It's going to be poisonous. You don't want to inhale that thing. You don't want it leaking into a room. They're all pretty similar reasons. Question 8.5 says to explain why the reactivity of the halogens decreases going down the group. Well, we know that the halogens, group 7s, are trying to pull electrons in. And we know that this is getting more difficult because the outer electrons are further from the nucleus. Because they're further away, the nucleus has less attraction. To those outer shell electrons. And that means they're gained less easily. Anything that's a non-metal, going down those groups, they always get less reactive, and the reasoning behind that is always these 3 points. The outer electrons are further from the nucleus has less attraction to the outer shell electrons, and the electrons are gained less easily. And all the group 1 metals, group 2 metals are the opposite explanation here. Well, their outer electrons are closer to the nucleus, they have more attraction to those outer shells, and they are losing, they're more difficult to lose those electrons when they're closer to the nucleus as well, and that's why we can say this. Question 8.6 says, a teacher, when we complete this reaction, okay, the first thing that we need to do in question 8.6 is we need to work out how much iron and how much chlorine there is in our substances and the ratio between them. So to work that out, we can look at our results over here. Next to this table, we can work out how much iron we have by looking at the difference between the glass tube and the iron. We can work how much chlorine we have by looking at the difference between these two, because the amount of iron won't have gone up or down. Any extra in that final section should be the chlorine. Now we know that the difference here is 4.48. And we know the difference here because we can work it out. It's 8.52. We now need to work out how many moles of each of those things we have. Now we know that iron is 56, and we know that chlorine is 35.5. So if we do 4.48 divided by 56, this gives us a number of moles of 0.08. If we do 8.52 divided by 35.5, it gives us an answer of 0.24. How many times does 0.8 go into 0.24? It goes into it 3 times. So we have a 1:3 ratio. So we know that the iron chloride that we end up making is going to be FeCl3, because it's a 1:3 ratio within that compound. Then we have to balance this symbol equation because you can't just leave it unbalanced. We've currently got 2 chlorines. That's 2 chlorines. That's never going to go into 3. So if we double this, we've now got 6 chlorines on the right, 2 ions on the right as well. So if we have 2 ions here, we need 2 ions here. If we've got 6 chlorines here, we need 3 lots of chlorine there. So our final equation is 2Fe plus 3Cl2 makes us 2FeCl3. And that's all we had to do in that question. Question number 9. So the question's about citric acid. And we had to read through this information here and look at the method. I'll come back to that in a second. Figure 6 shows an anomalous point where 0.6 grams of citric acid was added. This was caused by a student making an error. They correctly measured the mass. They correctly read the thermometer. They correctly plotted the point they were given. So we need something in the practical here they didn't do when they were mixing together those compounds to try and react all the substances there. Well, the only thing they may not have done here is they may have forgotten to stir the solution. You may have said they may have measured the temperature before the temperature stopped falling, or they may have measured the temperature too soon, was also a reasonable answer to mention here, because you might just measure it before that temperature stops changing, miss out on some simple marks. Question 9.2, to explain the shape of the graph in terms of the energy transfers taking place, you should use data from figure 6 in your answer. Well, if we look at the actual graph here, we can see what happens. We can see our temperature dropping and then increasing again. Now we know that when the temperature is dropping, this is likely because our reaction is happening, and the reaction isn't going to suddenly become exothermic. So there must be another reason why that temperature is starting to increase. We'll have a think about that in a second. To start with, we know that temperature decreases initially because energy is taken in by the solution. Temperature decreases initially because energy is taken in by the solution. We then know the temperature starts to go up, and that does that when the 1.5 grams of citric acid has reacted. And we know that the only reason where that extra temperature must be coming from is the surrounding, is the room. So it's the temperature of the room that's then increasing, is transferring energy. No, it's increasing, that's the wrong phrase to use. Let me reword that. We can say that it is the temperature increasing as energy transferred from the room to the solution. The temperature then increases as energy is transferred from the room to the solution. And that's why that temperature goes up the way that it does. Question 9.3 says a second student repeated the investigation using a metal container instead of the polystyrene cup. The container and the cup were the same size and shape. Sketch a line on figure 6 to show the second student's result until 1 gram of citric acid had been added at the starting temperature. The solution was the same. Explain your answer. Now, we know that metal is not as good at insulating heat, so our temperature change is not going to be the same, even though we're using the same substance. We're just using a bit less of it because the container is now metal. The metal is a better conductor. This means more energy is absorbed from the surroundings. And it means that our reaction is still going to start at the same temperature at 16.8, but it's going to stop at one point, but it's going to be less steep. A straight line again, I could do that with a ruler, and that's a bad way to do it because I shouldn't go over it multiple times. It's going to be a single straight line. I don't actually have a ruler here with me. From 1 to there. You do that with a ruler. I don't have one that I can use on my screen currently. And that's all because the metal's a better conductor, so the metal, the more energy absorbed by the surroundings. Absorbed from the surroundings, sorry. Irritating that it just deletes all that. More energy is absorbed from the surroundings is what you need to get from it. Right, in this question, we have a 0.05 mole per decimeter cube solution, and we've got 250 centimeters cubed of that. So we've got a quarter of a 0.05 mole per decimeter cube solution. So we need to work out how much we have of our citric acid in that solution. Our first step here is going to be work out the molar mass of citric acid, which is C6H8O7. So we're going to do 12 times 6, because we have 6 carbons, and carbon is 12. We're going to do 1 times 8, because that's hydrogen, and hydrogen has a molar mass of 1. That should be 72, that should be 8. And we're going to do 16 times 7, because that's oxygens. And 16 times 7, it should be 112. Once we've got those, we're going to add them all together to get 192. And we can then work from there, because 192 will be 1 mole of that solution. So we then need to work out what 0.05 moles would be. So 192 times 0.05 is 9.6. And that would be if we had 1,000 centimeters cubed. If we had 1 decimeter cubed, that's how much of that we have. But we haven't got a decimeter cubed, 1,000 centimeters cubed. We've got 250 centimeters cubed. We've got a quarter of that solution. So we're going to divide this by 4 to give us an answer of 2.4 grams. And that's the answer you should have got for that question. Question 9.5. said, describe how the student would complete the titration. It starts here, measure 25 centimeters cubed of sodium hydroxide into a conical flask using a pipette, add a few drops of indicator, fill the burette with citric acid. Our next step was going to be to add the citric acid until there is a colour change. We could record the volume of citric acid added. And we would also swirl while we did this. And use a white tile. So you can see the colour change better. Also repeat and calculate a mean. when you're doing a titration, those points are essential. Those last three, you must swirl, you must use a white tile, you must do it 3 times and get a mean from your results. You could also add in there that you'd add the citric acid drop-wise when you get to the end to make sure you don't miss any out as well. Again, that's really, really important. Question number 9.6 said, give 2 reasons why a burette is used for citric acid. Well, we can add citric acid in small amounts. Or increments, small amounts each time and stopping. You can measure volumes easily. We call them variable volumes. And it's more accurate than measuring cylinder. All right, in this question, we need to work out how many, or what the concentration is of our unknown substance in this titration. In titrations, we should always calculate this in the same way. It's really, really simple. We're going to use a table method. We know we're working with citric acid and sodium hydroxide. That's the first half of the equation. We don't care about the last half, so we can scribble it out. We're going to write out that first half of the equation there. And we're then going to need a 4-row table. And everything split up into those 4 rows for us to work with. The first of those should be the concentration, followed by the volume, the number of moles, and the ratio. And we're going to plug our numbers into this one from the table above. It says we have 13.3 centimeters cubed of 0.05 mole per decimeter cube citric acid. So our concentration of citric acid is 0.05. We know that our volume of citric acid is 13.3 centimeters cubed, but because our concentration is in moles per decimeter cubed, all of our volumes also need to be in decimeters cubed as well. So we're going to do 13.3 divided by 1,000, which is 0.0133. So we're then going to do 0.05, and going down the table here, we multiply things together. We're going to multiply that point by 0.0133 to get an answer of 0.000665. We then are going to look at the ratio. Now we look at the numbers in front to work out our ratio, and there's no number in front of the citric acid, so we're going to put a 1 in this column. There's a 3 in front of the sodium hydroxide. We're going to put in 3 in this one. And what that means is however many moles of citric acid we have, we'll need 3 times as many moles of sodium hydroxide to neutralize it. So we have 0.000665. If we multiply that by 3, we get a number of moles of 0.001995. 0.001995. We then are going to look at the number of moles we have of sodium hydroxide, which is 25. Obviously, you would divide that by 1,000 again. And 25 divided by 1,000 is 0.025. And we can then go back up the table, and because we're going concentration now, we went down the table, we multiplied. Going back up the table here, we divide. We're going to do 0.001995 divided by 0.025 to give us an answer of 0.0798 moles per decimeter cubed as our final answer to the question. Using the table method is how you should always be doing this one. Make sure you filter those into your papers. If you have any questions, keep them for when we come back after in our next lesson. You can ask about them in break times. Come find me and I'll answer any questions you have about those things. We're doing lots of practice on these things as well, because these are all things you need to get your heads around ready for your mock exams in December. Thanks for watching. Goodbye.